Okay, so let's get started. Any questions? So you're back to your regular schedule in terms of recitations today. So your TAs in your respective sections will do the recitation today. So and remember, today is the last recitation before the uh, current homework is due. So make sure that you make good use of uh, today's recitation and have all your questions answered. Any other questions? No?
I have a quick question.
Yeah.
Calculator won't be needed for the next midterm, right?
So whenever a calculator is needed, it will be available on the Lockdown browser itself.
Okay.
So you'll never need, and probably not. Okay, so most likely you won't need a calculator, but if you do, then it's, so I presume that if you have to multiply, do simple arithmetic like 4 times 6 or 8 times 8, you can do that in your head. But anything more complex, if it's needed, then we'll make the calculator available. Okay.
Okay.
So any other questions? So you have your schedule ahead of you. So I'll post the next homework like on Monday, so that you again have a chance to have the homework covered during your next recitation. But my expectation is that the next homework will be shorter than this one. Okay, so hopefully they'll, although it's back to back, because it's going to be shorter, hopefully it'll be fine. Any other questions? Okay, good. So let's start. Pick up from where we left off. So so last week we were discussing this game, and how you have this unintuitive result that although it seems like your original choice of which door to pick should be as good as a new choice, it turns out that by switching your choice, you in fact increase your likelihood of winning significantly, right? So instead of having a probability of 1 by 3, you have a probability of 2 by 3, right? So that's interesting. So we went through the process in a systematic way. So hopefully at the end of it, you are confident that the answer is correct. But that's not the same thing as saying we understand the answer, right? So we'll come back to this question, maybe later today, or more likely in the next lecture on Thursday. And then we will understand exactly why we get this unintuitive result. Okay. But then before that, let's look at more fun problems, right? So there is a unusual type of dice that a stranger comes to you and tells you, hey, I have these unusual dice, and I want to challenge you to a game, right? So let me pick one of these dice and you pick one of these dice, and we will both roll, and whoever gets the higher number wins, and the loser pays the winner some money, right? So to sweeten the deal, he says you pick your die first. Okay, so so you get to choose which one to pick, right? So you can see that they all have they are unusual in that they don't have the usual 1 through 6 counts. Okay, And also assume that the opposite faces, right, that the faces that you cannot see are exactly the same. That is, opposite of this face will still be 1, right? So so there are 6 faces, but only 3 distinct numbers. Okay. So you can see that they are different in the sense that, it's not 1 to 6, but the numbers on each of the faces are different. So if someone tells you, challenges you to this game and says, you pick your die first. Okay, so you might say, look at this and then say, okay, let me focus on A and B. And, maybe you would say that B has a really high count, and maybe that puts you at an advantage. Okay, and so you pick B, and then the stranger is going to pick A. Okay, and then you play. Okay, and who has the higher probability of winning? Well, obviously A, right? Because otherwise the stranger is not going to come to you and challenge you to your game unless he's sure of winning, right? So let's try to understand why that is. And once again, we are going to draw the same old pictures, right? So the tree diagrams. Okay, so let's try to draw the tree diagram. Okay, so there are 3 outcomes, right? Let's say you roll the die B, right? And we are making the assumption that the die is fair, meaning that all 6 faces are equally likely to come up, right? So let's say, so you roll B, and there are 3 possible outcomes. You roll, your roll is 1, right? Or your roll is 5, right? Or your roll is 9, right? So these are the, for the die B, those are the 3 faces, right? So, so this column here is die B, right? So now suppose A rolls. So A has, again, 3 possibility, right? So A can roll either a 2, 3, or 7, right? So same way, 2, 3, or 7, and 2, 3, or 7, right? So now let's look at who wins, right? So we have tried. So in this case,
Isn't it
right?
2, 6, and 7?
I'm sorry.
Isn't it 2, 6, and 7 for A?
Yeah, I don't know why I said 3. Yeah. Right. So so each of these have a probability of 1/9, right? So because each of these edges have a probability of 1/3, and then once again each of these have a 1/3 probability. So each leaf here corresponds to a probability of 1 by 9, right? So let's talk about, B wins, right? So that is the event that's of interest to us, right? And in this case, so B wins. So you have chosen B, right? So if you look at, in this case, A is 2, B is 1, right? So in all of these three leaves, B is lower than A, right? So B is not going to win in any of these three cases. So now, if you look at these three, right? So B wins here, B wins here, right? Because I'm sorry, I'm just I just changed everything around. Okay, so so in this case, if B rolls a 5 and A rolls a 2, then obviously B wins. So B wins here, right? B loses in these two cases. And finally, when you come to this transition, B has rolled a 9. Therefore, 9 is going to beat 2, 6, and 7. So in all these cases, B is going to win, right? So B is going to lose in these cases, right? So this is all right? So B wins, or we can say B loses with probability right? So so you pick B. Unfortunately, your probability of losing is higher than half, right? So you expect that if it was just a game of chance, then you had a 50-50 chance of winning. Now you have less than 50% chance of winning, which means that you are you're a sucker, and somebody took advantage of you, right? So so then the stranger says, okay, maybe you didn't choose right. So let's double the game. Okay, and the rules are same. You get to choose which die to pick first, right? So you pick first. And so, well, of course, you'd say, hey, A won over B. So let me pick A. Okay, so that's the game. And then the stranger says, you know what, I'm going to pick C. Okay, and let's work through, we can work through the specifics, but can someone tell me what's going to happen, and explain why, okay, so just tell me what do you think is going to happen in this case? Right, so you pick, right, and the stranger picks C.
Uh,
so if you pick a 2, you'll lose all the time. If you roll a 6, you will lose 1/3 of the time, and if you pick a 7, you'll lose 1/3 of the time. So I think you're still more likely to lose than win.
Right. So let's draw the picture again. So what you just said. So let's again say, A rolls something and C rolls something, and let's say C wins, right? So so A can do either a 2, six, or 7, right? And then C rolls either three, 4, or 8. And you can see that since A rolled a 2 in this case, C is going to win with any roll, right? So C wins in all 3 cases. Now, A has rolled a 6, so the only way for C to win is if C rolls an 8, okay? Similarly, if A rolls a 7, once again, C can win with only one of the rolls, and so C loses in 4 of these cases, but C wins with probability of 5/9, right? So once again, you have been scammed, right? So you lost again, okay? So now the stranger tells you one last time, right? Double or nothing. You can go again first, okay? So what are you going to choose this time?
We've tried A, we've tried B. Looks like we have to try C now.
Right. Okay. So let's try C now, right? And what do you think the stranger is going to do?
I think dice B in this case. Choose dice B.
Well, obviously, it wouldn't make sense for the stranger to choose A because that's obviously a losing game. So the only meaningful thing to try is, so let's see what happens here, right? Let's draw the picture again. And right, so once again, C can roll a 3, 4, or 8, right? And so B can roll a 1, 5, or 9, right? 1, 5, 9, 1, right? And we can see that here C wins because C rolled a 3, B rolled a 1. But these 2 cases, C, has only a 3 and B has higher. So similarly, over here, C has 4. Therefore, C is going to win in this case when B rolls a 1. But if B rolls a 5 or a 9, once again, C loses. And in this case, well, C has a high score. So once in this case, C is going to win if B gets a 1 or a 5, but C is going to lose when B scores a 9, right? So C wins with probability 4/9, and once again you lost, right? So does this make any sense to you? At a higher level, I understand that the picture, the analysis makes sense, and you're convinced that, the results we arrived at is correct. But my question, if I can see more of you. Can more of you turn on your cameras? Okay, so this game seems strange, right? So no matter what die you choose, the stranger is able to choose another die and always win, right? So that does not seem intuitive, does it? So what is strange about this? Why do we call this a strange dice? Not just because they have, unusual numbers. I don't know that game. What is this game of dots and boxes?
It's a game where it's a board of all dots, like a grid of dots.
Yeah.
You draw a line between two dots, and your opponent draws lines between two dots as well. Whoever makes the final line that creates a box gets a point. And it's one of these kind of games where, depending on who goes first,
Yeah.
Unless you are really good at it and know the secret tricks, there's no way to win if you go first.
Okay, so yeah, definitely there are games where the person who goes first will always win, or the person who goes first will always lose, right? So this is clearly one of those games, right? But what is unusual? But in those games, it's not very I don't think there is anything that we find particularly unintuitive that either the person starting the game or person who goes second has an advantage, and we don't find that necessarily that there is any kind of contradiction in that, right? But right here it seems, what do you expect in a game like this when you have 3 dice with different counts? You expect what property to hold?
I think you'd expect some kind of like best die, but we don't really have that here.
So we kind of expect this, this die is better than the other die to be a transitive property, right? So we expect that if die B, if die A is better than B and C is better than A, right? So we look at it this. So our experiment so far said, A is better than B, right? And we also did the analysis that showed, C is better than A, right? So we know both these things, and we expect this relationship to be transitive, which is why from this we concluded that C should be better than B2, but in fact that's not the case, right? This is happens to be not a transitive relation, right? So that seems very unusual, right? Doesn't seem very intuitive. Can you look at the dice and sort of see if there is anything there that see, after all, these are numbers, right? So we say we have this expectation of transitivity because the relationship of greater than on numbers is of course transitive, right? So we expect that if C is consistently able to come up with better counts than A, then and A is able to consistently come up with better counts than B, then it almost seems like it's just a relationship on numbers, and therefore it should be transitive, right? But it is not. So can you think of any sort of explanation as to why we are getting this unusual result, some counterintuitive result? Anything you can observe about the dice that?
No, wait. Okay, so maybe I'm wrong here, but
That's fine. Yeah, go ahead.
die C,
Yeah.
it has a lower low, it has a higher low and a lower high than the other two dies. No?
Higher low and lower high. Not okay. So
I don't.
see, A has the highest on A is 7, right? And the highest on C is 8. So it's you are getting somewhere, although maybe you're more ambitious than what you can actually show.
I think like as far as like the dice go, like if you pick B and then A, right? B has more sides which are, A has more sides which are higher than B, in the sense. I don't know how to word it, but A only has one biggest number which it can win with, and C only has one biggest number which it can win with.
Right.
That's
So
really
one
all
thing
that
that
matters.
have you looked at what is the total on all the dice?
Oh no.
So the total on each die is 15, right? That kind of tells you that the combined, strength of these dice are, or if you keep casting them many, many times, right? And then you add up the numbers, you should get basically the same number, right? So let's say you go on and play a game where you say, you know what, we are going to pick our dice, but we are going to roll 100 times each, and we are going to add up the numbers, right? So then what do you think will be the probability, right? So whoever wins at the end of 100 counts, wins, right? So you add up over 100 times what numbers you get, and whoever gets more at the end of 100 times, then he wins. Brian?
So looking at the relationship between the numbers between
Yeah.
C and A, 2 of their numbers are 1 greater than A's, but for A, the third number is 2 greater than C, and that's also between A and B B and C. So it's almost like when you're comparing C and A, even though they add up the same total, it's like C has more efficient numbers against A, and A against B, and B against C.
Right. So there certainly are ways to explain why we get this strange result, but not necessarily a clear explanation as to why this kind of greater than relationship, which seems to so closely follow the numbers, behaves in a counterintuitive way here. So let's try slightly different game, right? So the stranger says, I'm sorry I got you, but this time let's play a fairer game, okay? Because if you just roll once, there is too much to chance. Okay, so let's try rolling twice. Okay. And this time, the stranger says, I know you're not going to go first, so I will go first. Okay. And then you go second. Okay. So let's see what happens if we roll twice and we add up the numbers. Okay. So drawing the diagram is going to be a little bit more difficult because if you roll twice, then there are 9 possible outcomes, right? So if you have to draw a 2-level tree with 9 times 9 edges, then that's going to be a really large tree, right? So so what I will ask you to do is so let's see if we can do it, right? So maybe we won't draw both of the levels, but somehow try to estimate without showing the entire level. So so let's say we roll A twice, right? So if we roll A twice, then you could get the scores you could get are okay, so you can get a 4, you can get so right, so if you roll twice, you can get a 2 both times, so your total will be 4, or you can get a 2 and a 6, in which case you'll get an 8, or you can roll 2 and a 7, and then your total will be 9, right? Then you could get, oh, there are only 6 outcomes, right? So I don't know why I said 9, but that's okay. So the next is you could get a 6 and a 6, so that's 12 or 13. So the number of combinations we have is 3 choose 2, right? No, I'm sorry. So that's not correct. So the number of choices is actually okay, so let's right, so those are the possible those are the 6 possible outcomes, right? So you can roll the same phase twice. So that gives you 4, 12, or 14, right? Or the other possibility is that you roll a different number. Okay, so the probability of producing a 4 is 1 by 9, right? Because you have to roll a 2 both times. So similarly, you can say that the probability of this is 1 by 9, and this is 1 by 9. But the probability of producing an 8 is higher because you can roll either a 2 and then a 6, or then a 6 and a 2, right? So therefore, the probability for the other 3 is 2 by 9, right? Because again, you can just list what are the outcomes that are possible, right? So you can have a 2, 2, 2, 6, 2, 7, right? Or your first can be a 6, 2, 6, 6, 6, 7, or 7, 2, 7, 6, 7, 7, right? So these are the 9 possibilities when you roll the die twice, right? So so this one adds up to 4. This one adds up to 12. This one adds up to 14. And you have 13 being produced in 2 different cases, and 9 being produced in 2 cases, and 8 being produced in this many cases, right? So now you can see what we can similarly draw, what happens if B rolls twice, okay? So if B rolls twice, once again, you can do, 1, 1, 1, 5, 1, 9, or 5, 1, 5, 5, 5, 9, 9, 1, 9, 5, and 9, 9, right? So this is 2, 6, 10, 6, 10, 14, 10, 14, 18, right? So we have, we are producing 1, 2, 3, 4, 5 outcomes in this case, right? Because somehow, 9 and 1 add up to the same value as 5 and 5, right? So the number of outcomes for B rolls is less. And so we see we can roll a 2 with a probability of 1 by 9. Then we can roll 6 with a probability of 2 by 9. Then 10 with a probability of 3 by 9. 14 with a probability of 2 by 9. And then 18 with a probability of 1 by 9. Okay. So now you can sort of try to put this tree, attach this tree at each of these leaves, right? And then try to calculate exactly what the probabilities are, right? And it's going to take some time, but if you work through the process, right, you will find something unusual once again, which is that, previously A beat B, but in this game, B square will beat A square, okay? And you can understand that as follows. right? So the point is that whenever you get this big number, right? So when you roll the dice just once, right? The fact that you got a 9 really doesn't help, right? Even if the highest count was a 8, right? In a single roll game, if you replaced this face of B with 8, right? That would not change anything, correct? Because 8 is still bigger than any of the counts on A, right? So it wouldn't have changed at all. But there is some benefit of having a 9 instead of an 8 if you're going to add up 2 counts, right? Because maybe the first time you got unlucky, you rolled a 1, and then the next time you rolled a 9, and together you get a more decent score of 10. And 10 is a good number as compared to A, because the only way of the 9 possible ways, 9 possible outcomes A can get, only 4 of them, right, will produce something higher than a 9. The 4 being, right? So you can see that the ones that are above 9 are 1, 2, 3, 4, right? So only 4 of the time you are able to produce about 10, right? Because so you can see that the fact that B has a high number here helps out when you have 2 rolls. But if you have just 1 roll, even if you make B have just an 8 on that face, it would not change the result of the game at all, right? So when you add up, then what happens is that the differences, there are 2 things that are going to happen. One is that the differences are going to become less pronounced because things tend to average out. So you will find that the differences this time are in the range of, like 2 by 81, right? So when you do this twice, the difference in probability is like 2 by 81, whereas in all these, the difference was like 1 by 9, right? So the stranger was going to win had a 1 by 9 probability about half, right, of winning. So whereas here the number will become much smaller because the because things tend to even out over a couple of times. So now let's try to answer so the question I have is that what's going to happen if I do this like 100 times? What do you think is going to happen? If I roll A 100 times and I roll B 100 times, what is the probability that either one will win?
It's a 50-50.
So what tends to happen is that when you do this so many times, then what matters is the sum of the faces, right? So if they're all 15, then you can see that if you keep rolling them, right, the total is going to be somehow, because each face is going to come up with the same probability as every other face, right? So roughly speaking, if you roll it 3 times, then you should get a 15, altogether, right? So no matter which die you use, if you roll it 3 times, chances are that you'll just get a 15, right? But of course, if you just roll it 3 times, then it may not always come up with different faces. So the actual number will vary. But one of the things about repeating experiments many, many times is that the outcomes tend to average out. So as a result, what you expect on average will match the result of rolling the die many, many times. So what you will find is that as you increase the number of times you roll, the probabilities, get very close to half, right? But the interesting property of this dice is that, if you roll an odd number of times, then that property holds. If you roll an even number of times, you can show that the exact so if you have even number of rolls, then the direction reverses, but they get closer and closer to half the more times you roll, right? So of course, it's hard enough for us to analyze when you roll twice. So I don't expect you to sit down and try to analyze when you roll 3 times or 4 times. But that's so you can just take it as a given that the strange dice has this unusual property. So let me ask you another question, right? So what do you think is the likelihood that 2 of you have the exact same birthday, right? Obviously not the year, but the month and date, right? So the month and day of month, right? So what do you think is the likelihood of finding 2 people with the exact same birthday in this class? Anybody wants to take a guess? Yeah, in this class, right? So there are 55 or 56 people in the class in CSE 150. Anybody wants to take a guess? Of course, it's, that if somebody guesses right, that won't be good, right? Because the whole point is to make people make incorrect guesses and then explain why it is incorrect. But still, we should take a guess. So what do you think? So there are obviously 365 days in a year, right? And there are 55 people in the class, which is like 1/7, let's say, roughly, right? So the expressed as a fraction of number of days in a year, it's about, this class is about 1/7 in that size. So what is the likelihood that 2 people have the exact same birthday? Okay, any 2, right? Doesn't matter. No, nobody wants to guess? Dylan.
I think you could solve it by taking the probability that they don't share the same birthday and then raising that to the power of the number of students and then doing 1 minus that.
So you want to tell me what that formula is, even if it's, we'll correct it if.
Okay, 1 minus 364 over 365 to the power of, and then the fraction goes to the power of, no, just the fraction.
Okay, sorry. Let's fix that.
To the power of 55.
Okay. So you think that's the number, right? Okay, so let's let me calculate what that number is. Just give me a minute. Okay. So let's try to understand what you said. And so you said 364 by 365 is the probability that people have different birthdays.
Yes.
And so what you're trying to do is to raise it to the power of 55 because
Yes.
you want to say that. So this number is going to be ultimately, so this is the probability that they have different birthdays. So this 1 minus that is in a sense going to tell you when they have the same birthday, right?
Yeah.
So this is 0.14, which if we did a sort of a simpler minded argument, we would just say, 55 by 365, right? Which is approximately 1 by 7 is the number that you are giving me, right?
Yeah.
Okay, so this is, so if you think about, what this is, right? So this is, of the form, right? So 1 minus x power n, right? So if you do the binomial expansion of that, that is sorry. Why am I writing? Right, so this is the binomial expansion of 1 minus x to the power n. And if x is very small, you can kind of ignore those, right? And so you'll get 1 minus nx, right? And so that is 1 minus 55 times I'm sorry, what I meant is that right? So this is nothing but 1 minus right? So this is the 1 minus x that I'm writing down. Okay, so if you want to compute 3 to the power 364 divided by 365 whole to the power 55, then it'll end up being right. So it's not that this number is somehow magically happens to be equal to the number you came up with. But in fact, if you expand this number, you will end up with exactly the same, almost exactly the same number. And that's why they match up. Okay. So, okay, so let's look for another guess. Right. So this is it's not that the thought process is in some ways right, but there is some key point that's being missed, and we'll come back to that later. Anybody else wants to try a different guess? No? Come on, you can do it. Why not? So have you any of you heard of something called a birthday paradox? Right. So the other term that is used for this is birthday paradox. So there is an answer on the chat. So I will pick that up later. But what I want now is like an answer, right? So something that, so one answer is 1/7. So what is, does somebody have a different guess? No. Okay. So what will you say if you know, so the correct answer is that it's virtually certain that there are two people in the class that have the exact same birthday. Okay. And in fact, all you need are 20 people in the class, right? Or 22 people in the class in order to have a 50-50 chance of having two people with the same birthday, right? By the time you have 55 people, it's almost a certainty. Okay, so now let's see, where are we going wrong? Okay. So the answer we looked at is almost right. But the key point that was missed is that, you know, there are so many pairs of people to consider, right? And for each pair of students, you can say that the likelihood that they would have different birthdays is 364 by 365. So that's not an incorrect calculation. But then there are n choose 2 pairs of people to consider, right? And if we assume that whether one pair shares a birthday is independent of whether another pair share the same birthday, okay, then we can use our usual rules on probability, which is we simply multiply the probabilities, right? So all we needed to correct is that we needed to raise it to the power n choose 2 as opposed to just n, right? So once you choose the right exponent, right? So then this ends up being a much smaller number, right? So in the case of, so in the last slide, we calculated 364 divided by 365 whole to the power 55 was approximately 6/7, right? Whereas if we do 364 by 365, (55) choose 2, right? Which is 364 by raised to the power of 1200 or so, right, approximately, then that turns out to be just 0.014. Okay, so there is from 6/7, it falls down to 0.014. Okay, so which means that so notice that what we are calculating is the probability of not finding two people with the same birthday, right? And that probability turns out to be just 1.46%, right? So there is a 98.5% probability of finding two people with the same birthday in the class. Okay, so now there is in fact this assumption that whether one pair of students share a birthday is independent of whether another two people share the same birthday. That's not an entirely correct assumption, but it is close enough that you get a number which is very, very close to the correct value. Okay, so here is a more accurate calculation. Okay, so the way to think about the problem is that if there are no constraints for n people in terms of their birthdays, then there are 365 raised to the power n possible sequences of n birthdays, right? So each person's birthday could be any of the 365 days. So if there are no constraints, then if I write out the birthdays of n people in a sequence, then there will be 365 to the power n possible such sequences. Okay, but if you say that we don't want the birthdays to repeat, then the sequences become smaller because the first birthday can be any of 365. The second one has to be one of 364 because I can't repeat the first one. And then the third one is going to be 363 because I can't repeat the first two, and so on. And so you end up with something that's like this. And this is kind of what was mentioned in the answer, although it's not exactly that, right? The expression looks kind of like what I have here, but it's not exactly the same. Okay, so now if you want to find the probability of having no duplicates, then you simply look at the number of sequences that have no duplicates and divide it by the total number of possibilities, right? Because we are thinking that every possible sequence of birthdays is equally likely, right? And then this tells you the number of sequences without repetition. This tells you number of sequences that include repetition. And so we divide one by the other, that'll tell us the probability of finding something without a repetition. Okay, so that's what we do here, right? So we divide this by 365 power n. And so we do 365 divided by 365, 364 divided by 365, 363 divided by 365, and all the way to 365 minus n minus 1 divided by 365. And then we simplify. So, so this is going to be just 1. And this is going to be 1 minus. So this one is, so this is nothing but 1 minus 0 divided by 365. This is 1 minus 1 divided by 365, right? Because this and this cancel out, right? So you can write it out as 1 minus 1 by 365. Similarly, you'll have 1 minus 2 2 by 365 all the way up to 1 minus n minus 1 by 365. And then there is this approximation which we can apply, right? So it's not something that you're going to dream up. It's something that you should know, right? So, so this is a known result that 1 minus x is less than or equal to e to the power minus x, okay? And if x is small, then this is actually a very good estimate, right? 1 minus x and e to the power minus x are very close if x is small. If x is large, then still the inequality holds, but the actual values may be a little bit different, right? So we use this to basically say that this quantity is less than this quantity, because all we have done is we have replaced 1 minus 0 divided by 365 by e to the power 0, 1 minus 1 divided by 365 as e to the power minus 1 by 365. Again, applying this particular approximation on each of the terms here, right? And then we end up with something like this. And now we have this product, and product is going to become a sum on the exponent. So that's what we have done. We have just summed up the exponents here, and you end up with an expression like this. And if you substitute the numbers, you'll get 1.47%. So whereas the more approximate calculation here yields 1.46%, right? And well, this is approximate too, but the point is that here what you have is an upper bound, right? Because notice that we are replacing every term with something that's slightly larger. So we are overestimating the probability that no two people have the same birthday, right? And that turns out to be 1.47%. But I do like this way of calculating because it sort of points out the main mistake that we tend to make, which is that we think of n people instead of realizing that there are approximately n square number of pairs to consider, right? And when we take into account that the number of pairs to consider is n choose 2, then we are able to arrive at more or less the right result. Okay. So again, so the birthday paradox is something that's interesting, and most people who know who are quite comfortable with probabilities and quite proficient still get are tripped up by this problem and end up making guesses like what we made in the class, like there is roughly 1/7 is the probability of finding two people with the same birthday, but whereas if you carefully work through the details, you end up with the result that there is nearly a 99% probability that there will be two people with the same birthday. So now let's, so much for these problems with unintuitive results. Let's try to summarize some rules for relating to probability, right? And let's talk about some terminology, right? So we introduced some terminology before, but let's introduce them in the context of sets, right? So we talk about a sample space, right? A sample space is simply a countable set, right? So that's what we are going to work with, right? So the set can be infinite, okay? Although most of the time we will be working with finite sets, right? So like all the problems that we have discussed in this unit so far, they are all on finite sets, right? So we're talking about tossing a die. There are a finite number of outcomes, guessing which door has a car behind it has a finite number of outcomes. We're talking about a finite number of people with, finite number of possible birthdays. So far we have only looked at the finite case, but there can be, but nothing that we are doing is limited to the finite sets. They can be applied to countably infinite sets as well, okay? So an outcome is just a fancy name to talk about one of the elements in the set, okay? So in the context of a probability, one of these elements will be called as an outcome, right? So for instance, if you think about the die game, right? So the space is the possible counts that you can get from different dice. And so each toss of the die is an outcome in the experiment that involves basically tossing, rolling dice, right? So that's why we use the term outcome when in fact we are simply referring to one of the possible elements in the set. So the set or the sample space simply corresponds to all the possible outcomes of the experiment that we are conducting, right? So whether the experiment is simply tossing dice or tossing coins and seeing whether you come up with heads or tails. These are all experiments with certain outcomes, and these outcomes, the set of possible outcomes is really what we call as a sample space. An event is simply a subset of this space. So for instance, if we toss 2 dice, right? So then the sample space consists of, all possible values of n1 and n2, where n1 is the count you get from the first die, and n2 is the count you get from the second die, right? So sequences like this, right? So you can get, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. Let's assume that there are only 3 different values, right? So then 3, 1, 3, 2, 3, 3. So these are the possible outcomes in your experiment, right? So the sample space is this, right? So this is this sample space. And an event could be that the first die produces a higher count than the second die. So that would be this one. So these 3 outcomes correspond to the event that the first die comes up with a bigger number than the second die, right? So that's why any event can be broken into a subset of the sample space, okay? So when we say event, we have some intuition behind that. That's why we say, the first die wins over the second die. That has some meaning to us. But when we express it in terms of set theory, it's just a subset of the possible outcomes, okay? And then we can define a probability function as something that maps, each outcome, right? So it maps each outcome, associates each outcome with a probability, right? And of course, probabilities have to satisfy 2 rules. One is that probabilities should always be greater than or equal to 0. And if you sum up the probabilities of all possible outcomes, that should add up to 1, right? So those are the 2 rules about the probability function, right? So so this way we can define everything related to probability in terms of what we already know about sets. So And now what we can do is we can, apply what we already know about sets to tell us about, probabilities of events, right? So for instance, we can say that E0 through En are pairwise disjoint events, okay? Remember that each of these is a set, right? Each of these is a set. So when we say pairwise disjoint event, that means we are saying that EI intersection EJ is empty set whenever I is not equal to J, right? So when we say disjoint event, we are saying disjoint sets. Okay, so that's the thing that you need to remember. Okay, so we know how to count the cardinality of the union of disjoint sets. We simply add up the cardinality, and so that's same operation is going to be applicable for probability as well, right? So probability of a union of n disjoint events can be computed by simply adding up the probabilities of the individual events. Okay, so it simply says that the probabilities of disjoint events simply add up. Okay, so complement rule, once again, this follows from the cardinality rule that says cardinality of A bar equals cardinality of the universal set minus the cardinality of the set, right? So the cardinality, the universal set corresponds to a probability of 1, which is what we said here, right? So because if you take all possible outcomes and the probability of, and you sum up the probability of all possible outcomes, that's going to be 1. So if we take the probability corresponding to U, that'll end up generating a 1. Probability corresponding to A is just probability of A. So probability that A does not happen is 1 minus probability that A does happen, right? So this is, of course, a probability rule that all of you have known for the longest time. But when we think in terms of sets, we can derive this rule from what we know about sets, right? It's cardinality of sets. And the same way you can, go on with the other rules. So the difference rule says probability of B minus A, right? Which is the same thing as B happens, but A does not happen, right? So that's how you interpret B minus A, right? So what is the probability that B happens, but A does not happen, okay? And because both B and A are sets, the probability that B happens and A does not happen is as if you think of it as a set, then it is like a B minus A, okay? And once again, you can apply this, which basically says you take the probability of B and then you subtract the probability that both A and B could be true, right? So this is, again, we know from our Venn diagram picture, right? So this is, let's say this is B, this is A, right? So B minus A is this, right? So to get to B minus A, what we are going to do is we do cardinality of B minus right? So what this picture illustrates is that the cardinality of B minus A is nothing but the cardinality of B minus the cardinality of A intersection B. And that's exactly what this probability rule tells you, right? So essentially and then we talked about the inclusion exclusion principle for computing the sizes of the size of the union of two sets. And the same thing applies to probabilities as well. The probability that A happens or B happens is the probability of A happening, and then you add up the probability of B happening, and then you subtract the probability that both of them happen. Okay, so so essentially what we saw as inclusion exclusion principle on sets is also applicable to probabilities, and then these two rules are also fairly easy to understand. Monotonicity says that if A is a subset of B, then probability of A must be less than the probability of B, right? And similarly, probability of A union B is less than the two added up, which immediately follows from this rule, right? Because probability of A union B is obtained by adding this and then subtracting something, right? And therefore, if you just delete this negative term, then what you will have here is going to be, could be greater than what you have on the left-hand side, right? So the union bound is sometimes useful because sometimes you cannot figure out what is A intersection B. And then you can say at least I can derive a bound on the probability of A union B by simply adding these two values. Okay, so let us stop here, and we'll pick up on Thursday. Okay, very good. So if there are any questions, I'll take them. Otherwise, feel free to hang up and join your recitation in another 10 or 12 minutes. Okay.